Hello everyone, I am Sylvain Cordier, a postdoctoral fellow at LIRIT, and in this video I would like to present you a paper we are working on with Dr. Carl Thibault from the Quantum Institute, Professor Marie-Luc Carpin from the Management Faculty, and Professor Ben Amor from the Engineering Faculty and Director of LIRIT at the University of Sherbrooke. So this work is a comparative life cycle assessment between a quantum computer and a classical supercomputer. Some words to give you a bit of context. Emerging quantum computers are claimed to solve problems faster than classical computers or previously impossible to solve. However, it is unclear if quantum computing will surpass classical computing in terms of speed because classical computing keeps narrowing the gap with the quantum. Also, research indicates that quantum computers can have energy efficiency benefits. Quantum technology must deal with inherent noise in the physical qubit if the system is not well isolated, so it can imply error correction to create logical qubits. Typically, with tens to hundreds of physical qubits, there is a limited use of the computers without error correction. But scaling to tackle industrially relevant problems, it requires error correction. It is estimated that achieving practical quantum advantage could demand hundreds of thousands to millions of physical qubits. And finally, quantum computers have not been extensively studied for their environmental impact. Only a very recent master thesis carried out a rough LCA to estimate the impact of the production and the use phase. However, it didn't address industrial scale calculations nor the quantity of qubits, so no error correction was included. So to date, no research has compared the environmental impact of both computers, and the scope of this research is to understand according to the computing performance at a high level scale and according to the hours of use. How does the environmental difference between both computers evolve? To do that, we consider a powerful classical computer. So what you see is the most powerful computer currently available on the market. However, due to data availability, we used the following proxy to model the classical supercomputer, and it will be scaled to the supercomputer that I showed you in the previous slide. So it will be scaled to this supercomputer based on the number of processor cores. And here is one of the most prevalent platforms for quantum computing, which is made of 4 subsystems: the cryostat, which is a dilution refrigerator, a gas handling system, a compressor, and a control unit. So for the modeling, data mainly rely on the EcoInvent database, on data collection on site, on technical documentation and literature. And the system boundary is broken down into 4 phases: the production phase in blue, the delivery, the use phase, and the end of life. And this slide presents how the configuration is scaled to 100 logical qubits, which is a commonly used threshold where quantum computing will be able to perform computations that classical computing wouldn't. For example, for condensed matter physics problems. So for now, we have 2 scenarios to model a quantum computer which is relevant to compare with current supercomputers. So the first one would be more optimistic and the second more pessimistic. Of course, the scaling parameters may evolve in the coming years because they are crucial to achieving realistic quantum computer size and realistic energy needs. And for the classical computer, scaling based on the number of processor cores implies more than 12,000 compute blades. So we also consider a default scenario based on the number of compute blades for the sensitivity analysis. So this second scenario may seem less representative, but can serve as a lower limit. For the result, just to zoom on the climate change impact of the cryostat production, you see that considering the scale, so considering the number of qubits, it is relevant because the error correction contributes the most to the impact of the production of the cryostat. And when we compare the life cycle of the quantum computer at scenario A to the classical computer at scenario B, we notice a significant gap regardless of the hours of use. In the paper we are working on, you can find also the other scenarios, and we also present the impact on ecosystem and on human health. For the sake of transparency, some words on the current limits. More detailed data for modeling electronic components would be a plus. Also, a more specific functional unit for comparison could be the flop instead of the calculation time. And the lifetime of computers could be better addressed even if few information is available. For conclusion, we noticed a significant contribution of error correction equipment to the production impact of the quantum computer. Also, assuming equal lifetime, the number of computing blades and their electronic consumption make the classical computer more impactful. And despite the two main limitations, the modeling shows how one computer has an environmental advantage over the other. And future work could be about more analysis according to the quantity of logical qubits, the functional unit, the component lifetime, and the inventory of both computers. Finally, we address many thanks to our colleagues who provide assistance with the inventory and with the scaling. And if you want more information, the link of the paper we are working on is available in the description of this video. So that's all for me. Thank you, and I wish you a good day.